All right, this problem says a force Fx equal to minus 5x squared plus 7x acts on a particle. Now, here's something you need to be aware of. Force has units of newtons. X is in distance, that's in meters. So what are the units of this guy?
Newton meters.
Newton meter square. Okay. Each term has to be newtons. So this guy will have units of Newton per meter square, and this guy will have units of Newton per meter. Okay. So oftentimes they don't write the units, but you have to be aware of that. Okay. How much work does the force do on the particle as it moves from x equal to 2 meters to x equal to 5 meters? So the work done is given by this integral. From x initial to x final dx. Okay, so before we apply the limits, okay, so we'll write this as minus ux x initial to x final. And ux is the potential energy function. So ux would be 5 by 3 x cubed minus 7 by 2 x squared. Everybody understand that? And the reason for writing that is, remember, if you can, with conservative forces, you can define a potential energy function, and the work done is equal to ux final minus ux initial. Okay? And that's the idea. So this would be minus ux final minus ux initial. Yep. All right, so there's the potential energy function ux. Okay, and so let's evaluate this at these 2 points. X final is 5 meters, x initial is 2 meters. Okay, so the work done is minus u at 5 meters minus u at 2 meters. Okay. So u5 is 5/3, 5 cubed minus 7/2, 5 square minus 5/3, 2 cubed minus 7/2, 2 square. Okay. That is 125. I got 625 by 3. by 3, and that is 25 times 7 is 175 by 2 minus 840 by 3 minus 14. All right, so you can calculate that. So here is the potential energy function that they ask you in part B. Okay. So part B says picking a convenient reference point of the potential energy to be 0 at infinity, at x equal to infinity, find the potential energy. So there's the potential energy function, and let me show you a graph of that. Okay, so okay, this potential energy function. So the x cubed term overwhelms this for large x. Okay, so this graph looks like x cubed for large x. Okay, and x squared term only matters for the small values of x. Okay. So that's that function, and they ask you to make the potential energy, find the potential energy 0 at x equal to infinity. You can't choose a constant to make it 0 at x equal to infinity. So that's a typo in the problem. Anyway, so this is the potential energy function. Okay. And a potential energy of, anyway, so there's the curve. Okay. All right. This problem says a boy throws a ball of mass 0.25 kg straight upward with an initial speed of 20 meters per second. When the ball returns to the boy, its speed is 17 meters per second. How much work does air resistance do on the ball during its flight? Okay, air resistance, what kind of force is it? Is it a conservative force or a non-conservative force?
Non-conservative.
It's a non-conservative force. Work done by conservative forces can be accounted for by potential energy. Okay. Work done by non-conservative force cannot be written as difference in potential energy. Okay. Okay, so that's the difference. So work done by conservative forces is very easy to calculate. Okay. All right, so now if you check your notes, you'll see that work done by non-conservative forces is equal to change in mechanical energy. So kinetic energy plus potential energy final minus kinetic energy plus potential energy initial. Okay. What kind of work does friction do? Positive or negative? Okay, so air drag is a friction, it'll do negative work. So final potential and kinetic energy should be less than initial kinetic and potential energy. Okay? So this fellow is throwing the ball up at 20 meters per second. And the ball comes back, and it comes back to the same spot at 17 meters per second. Okay. Gravity is the only other force acting on it. So gravity acts on it and air resistance. Gravity is a conservative force. The work done by gravity is taken care of by the potential energy term. Okay. And what is the gravitational potential energy? mgy. Okay. So since the initial and final y position are the same, this cancels. Okay. So the work done by the non-conservative force, which is air drag, equal to final kinetic energy minus initial kinetic energy. And that's equal to 1/2 mv final square minus 1/2 mv initial square. Okay. So work done by the drag, air drag is 1/2 0.25 kgs, and V final was 17 square minus 2. Okay. And that'll work out in joules. Okay, so the drag forces, what this is saying is the drag forces reduce the mechanical energy by 13.9 joules. Okay. What happened to that energy? Energy is not created or destroyed, so what happened to that energy?
It was converted into energy, like thermal energy.
Yeah, it was converted to heat. Okay, that's what friction does. All right, so in this problem, you'll have two conservative forces acting, the two that you know. What are the two conservative forces?
Gravity and the springs.
Yeah, so this ball is going up and down, its gravitational potential energy is changing, and when the spring is compressed and uncompressed, the spring potential energy is changing. Okay. So the massless spring of a spring gun has a force constant of 12 Newton per centimeter. So K is 12 Newton per centimeter. We want to convert that to SI units, 12 Newton per 10 minus 2 meters equal to 1200 Newton per meter. Okay, that's the spring constant. It tells you how stiff the spring is. So what this means is, so most of our weight is about 600 newtons, 60 kg times 10. So two of us would have to stand on the spring to compress it 1 meter. 1 meter is that much. Yeah. Okay, they say when the gun is aimed vertically, a 15-gram projectile is shot to a height of 5 meters. Okay. So you compress the spring and then shoot it, and it goes up 5 meters above this uncompressed height, above the end of the expanded spring. How much was the spring compressed initially? They want you to find D. Okay. So we'll say E final. Okay, so in this problem, there's no air drag or anything, so mechanical energy is conserved. Okay, mechanical energy initial with mechanical energy final. That is kinetic energy plus spring potential energy plus gravitational potential energy is equal to kinetic energy final plus springs potential energy final. Okay, what is the initial kinetic energy? Zero. You fire the bullet from rest, and when it gets to the very top, it's at rest. So that is 0 and that's 0. Initially, so for the gravitational potential energy, we'll take this to be y equal to 0. Okay? And so you have spring, the initial gravitational potential energy is 0. Initially, you have spring potential energy. It's compressed that much. And that's equal to, in the final configuration, the spring is uncompressed, so spring final potential energy is 0. Okay. And so initial spring potential energy is equal to final gravitational potential energy, mg. And how far did it rise up? 5 meters plus d meters. Okay. All right, so now we can put in the numbers. 1200 d square plus, it's 15 grams with 0.015 kg times 9.8 meters per second square times 5 plus d. 600 d square Okay, so there's a quadratic equation, and we can solve for D. All right, so the solutions are D is minus B, 0.147 plus or minus B square, which is minus 0.147 square minus 4AC divided by 2A. Okay. All right, so D is 3.151 centimeters, about 1.5 inches. So you compress the spring about 1.5 inches, and the ball is shot up 5 meters. 5 meters is about 1.5 times this height. Okay. What is this other solution? See, a quadratic equation always has two solutions. What do you think this negative solution is? And it's slightly less than that. Okay, now this is a little hard to figure out, but what this means is, see, we've set up the equation where this D is positive in this direction. So this negative D, what that means is, if the ball were attached to the spring and you fired it, it would, if it was attached, it would rise up 3.49 centimeters above this point and then stop. Okay, so that's that solution. Okay, so this problem says a single force Fx equal to minus 4x. So this is like a spring force. There's the spring constant. Acts on a 1 kg body. When x equal to 3.5 meters, the speed of the body is 4 meters per second. What is its speed at x equal to 2 meters? Okay, that's a single force acting on the object. And what we're going to use is the work energy theorem. The work energy theorem says that the net work done, that is the work done by all the forces acting on the object, and in this case, there's only one force acting on it, is equal to change in kinetic energy. Okay. So the work done by our force is Fx dx okay. And minus 4x dx from 3.5 meters to 2 meters. So this is the work done. So the work done is 16.5 joules. And work done should equal 1/2 mv final square minus 1/2 mv initial square. Okay. Mass is 1 kg. V final square minus 4 square. All right, so 16.5 equal to I'll cross multiply this. That's 33 equal to V final square minus 16. V final square is square root of 49 equal to 7. So the final speed is 7 meters per second. Okay. So here's what's happening. Again, this is like a spring, mass attached to a spring. And when the spring is 3.5 meters away, it's going at 4 meters per second. And when it's at 2 meters, it's going faster at 7 meters per second. Okay? So that's what's going on. Yep.
How do you know that x equals 2 meters is our final position?
It says when it's at 3.5 meters, the speed of the body is that. What is its speed at that position? So that's the initial position and that's the final position.
Does it matter if you assume one or the other?
Well, it won't matter in this case. Well, as long as the speed at that point is that, this will come out to 7 meters per second at 2 meters.
Okay.
Yeah. Yep.
So if you switched it like you were saying
Mhm.
and made it negative, we would still get 7 meters per second?
Yeah, everything is a square. So let's say 2, that would become negative. Oh, no, that would become negative. Final would be smaller. No, it will matter. So this is the initial point and that's the final point. This is the initial point and that's final point. So if you switch the limit,
And then made it negative?
this will become negative.
Yeah.
The work is negative. This becomes smaller. Yeah.
Because I'm only asking because if you're looking at a number line, it would look to me that 3.5 meters is the final position. That's just
Right.
what they gave you. But if you're saying since it's first,
Mm-hmm.
I'll take it.
So that's what's implied from the statement. Okay. Well, for a spring, the further out, see, this is the equilibrium position. So as the smaller number makes it go faster. Yes, so. All right. This problem says a 60 kg skier with an initial speed of 12 meters per second goes up a 2.5 meter hill. So 2.5 meters is roughly the height of this room. Yeah. Find her final speed at the top, given that the coefficient of friction between her skis and the snow is 0.8. Okay, so there's friction. Okay, if there was no friction, she would still slow down because some of her kinetic energy is being converted to potential energy. Okay, and then in addition, the friction force will slow down. Okay, so when she's on top of the hill, there's a friction force. Okay, and it's a kinetic friction force. Okay, so you have non-conservative forces acting, and the work done by non-conservative forces is kinetic energy final plus potential energy final minus kinetic energy initial plus potential energy initial. What kind of potential energy do you have?
Gravity.
Gravitational potential energy. Okay. We'll take this level y initial to be 0. Okay, plus 0. Okay, now let's calculate the non-conservative, the work done by non-conservative force. Okay, so the friction force. It's friction force, so there's the friction force, and the distance traveled is s. So the work done by non-conservative force is minus the friction force. Well, it's friction force. Friction force always does negative work. S times cosine 180 degrees, which is minus FKS. Okay. S is this length. Okay. And so S is sine 35 is 2.5 divided by S. S is that distance. So S is 2.5 meters divided by sine 35. Okay, so the length of the slope is 4.6 meters. So roughly from half the room to the ceiling. That's how the slope is. Okay. Well, what is the friction force? So let me draw another diagram here. So here's the skier on the slope. There's mg. This is theta. This is mg cosine theta, which is equal to the normal force. And so Fk, the friction force, is mu k times the normal force. Okay. So now we'll put all of this in there. So Okay, so notice something neat here. The mass canceled. What does that mean?
For that given initial velocity, mass doesn't matter.
So every skier for that slope, for as long as the coefficient of friction is the same, every skier, well, so the velocity of every skier at the top will be the same. Okay? So the mass doesn't matter, okay? All right, so V final is what we are calculating. The initial speed is 12 meters per second. Okay, so we'll multiply everything by 2. So minus 2 mu k g cosine theta s equal to V final square plus 2 g y final minus V initial square. Okay, so this was the initial speed. This is how much you slowed down because you climbed up because of gravity. And this is how much you slowed down because of friction. Okay? That's what that says. Again, the square of all those things. Okay, so all right, so let's put in the numbers. 12 meters per second minus 2 times 9.8 times 2.5 meters minus 2 times 0.8 times 9.8 cosine 35. And what was S? 4.36 meters. Okay.
Charge your phone.
All right, so the final velocity on top of the hill will be 6.25 meters, 24 meters per second. Okay, this problem says a pogo stick has a spring with a spring constant of 25,000 Newton per meter. So like I said again, most of our weight is about 600 newtons, let's say 500 newtons, 25,000, that's 50 people would have to stand on that spring to compress it 1 meter. 1 meter is that much, so that's a very strong spring. Yeah. Which can be compressed 12 centimeters. To what maximum height from the uncompressed spring can a child jump on the stick using only the energy in the spring? If the child and the spring have a total mass of 40 kgs. Okay, so here's the compressed spring. Here's the uncompressed. And this is 12 centimeters. Okay, and what maximum height from the uncompressed spring? Okay, so this is what they're asking you. And of course, okay, so what we'll assume is the pogo stick has negligible mass, or this, so he's holding on to the stick, and that's where the center of mass of the child in the pogo stick is after. Okay. So this is the distance that you want, y. Okay. Again, there are two conservative forces acting, the spring force and gravity. Okay, so again, like we said before, when only conservative forces act, initial energy, mechanical energy is conserved. At these 2 points, kinetic energy is 0. So the spring potential energy at this point, we'll take this to be y equal to 0. And so this is y final. Okay. So spring potential energy, we'll call this x square, got converted to gravitational potential energy, mg y plus x. Okay. Everybody understand that? Okay. All right, so let's put in the numbers. 1/2, 2.5, 12 centimeters, 0.12 meters. Okay. .34 meters. 0.3 meters is a foot, so just a little over a foot. Okay. Okay, this problem says block 2 shown below slides along a frictionless table as block 1 falls. So there's no friction. That means non-conservative forces are absent. Okay. This block falls, its gravitational potential energy is changing. Okay. Find the speed of the blocks after they have each moved 2 meters. Okay. So after this thing has fallen 2 meters. Okay. Both blocks are attached by a frictionless pulley, and this is a frictionless massless pulley. Assume they start at rest and the pulleys has negligible mass. These are the masses. Okay, so initial energy equal to final. And that's kinetic energy of both the masses initially, kinetic energy of both the masses finally. Okay. This is 0. We'll say only this guy's potential energy changes, and we'll say the final potential energy, this is 0. We'll take this y to be 0, so it has only initial potential energy. So final potential, this is 0. So what is happening? Initial potential energy, the potential energy of this guy got converted into the kinetic energy of both the guys. Okay? So initial potential energy is m1 g y initial equal to 1/2 m2 v square. Their speeds are the same, 1/2 m1 v square. Okay. The potential energy of this guy does not change. Okay, so we don't have to track that. Okay. So this potential energy changed into the kinetic energy of the two guys. All right, m1 g y initial equal to 1/2 m1 plus m2 v squared. Okay. So 2 into 2 into 9.8. And what is y initial?
2 meters.
2 meters. And m1 plus m2 is 2 plus 4, 6. Okay, so v is 6, that is okay, so they're moving at 3.6 meters per second after having fallen 2 meters. Okay. if this guy was not attached and had this guy fallen 2 meters, would he be falling faster?
Yes.
Yes, this guy's holding him back, okay. Or some of his energy was given to him, so he's not moving as fast. Okay. All right. So this problem says, I'll probably just do one part of this. An object of mass 10 kg is released at point A, slides to the bottom of the 30-degree incline, then collides with a horizontal massless spring, compressing it a maximum distance of 0.75 meters. The spring constant is 500 Newton per meter. The height of the incline is 2 meters, and the horizontal surface is frictionless. This surface is frictionless. What is the speed of the object at the bottom of the incline? So the higher you release it, the faster it's coming. The faster it's moving, the more it'll compress the spring. So from the spring compression, you can calculate how fast it's moving. This surface is frictionless. Okay. What is the speed of the object at the bottom of the incline? So from the compression, we can calculate the speed here. What is the work of the friction on the object when it's on the incline? Okay, so on the incline, this has friction. Okay, so from the speed at the bottom, we can calculate how much work is done by the incline. Because if this was frictionless, that would correspond to a certain speed, all the potential energy being converted to kinetic energy. But if there's friction, this will be slower than on a frictionless surface. Okay. What is it at the bottom? What is the work of the friction? The spring recoils and sends the object back towards the incline, so it'll recoil. We won't do all those parts, so if you understand just the first two parts, that'll be good. Okay. So part A, so this is the configuration. And it's compressed the spring. Okay. So this is the initial energy, this is the final energy. Okay. Mechanical energy was conserved. Initially you have kinetic energy, and now what do you have? Spring potential energy. Okay. When friction is absent, when non-conservative forces are absent, mechanical energy is conserved. Okay. So V is K over M. And the spring constant is 500 Newton per meter. The mass of the block is 10 kgs. And the spring was compressed 0.75 meters. Okay. So the block was moving at 5.3 meters per second at the bottom. Okay. Now, I'll do a quick calculation. When an object falls through a height h, and if there is no air drag, 1/2 mv square equal to mgy. V is square root of 2gy. Okay. So if there was no friction and this mass fell 2 meters, the speed at the bottom should be, the speed at the bottom would be 2 times G is 9.8 times 2. (6.26 meters per second). Okay, and the actual speed was that. So friction slowed it down. Okay, did you guys understand this part? Okay. So the work done by friction, part B says, what is the work of friction on the object while it's in the incline? Part B, work done by non-conservative force, which is work done by friction, is equal to mechanical energy final minus mechanical energy initial. And work done by friction, okay, again, final mechanical energies, it has only kinetic energy, and initial mechanical energy is mgy initial. Okay. So that's 1/2 m. The mass of the block is 10 kgs. Its final velocity was 5.3 meters per second. And 10 kgs, 9.8 meters per second square. Initial height was 2 meters. So as promised, friction force, as we know, friction force does negative work. Okay. All right. Part C and D. Okay, so I'll just give you a indication. The spring recoils, so the spring compresses and then recoils. How fast will this guy be going at the bottom of the hill? It'll be going at the same speed because there's no friction. Okay. And if there was no friction on the incline, it would climb up back to that height. So if both this and that were frictionless, this would be a perpetual motion machine. Okay. All right. It's come back to that speed. Now because of friction, it won't climb as far. It'll climb only till there. And then let's say it falls back, compresses the spring, and then doesn't go as far. Comes back, okay? And so eventually it'll come to rest there. Okay, so that's what will happen. All right, guys.